Right, so in the beginning it was just me doing this kind of research, but over time a number of other people have joined in. We call ourselves the Causal Incentives Working Group, and this is our website, causalincentives.com, where we have all our papers and also recent alignment form sequence where we try to summarize our work at a high level. We've been working on things like defining incentives and manipulation, reward hacking, harm, decision theory, intent, all from a causal perspective. And sometimes people are a little bit confused why we insist on using causality for all these things. But I think for us it's quite natural, because if we want to make AGI safe, we want it to influence the world in a good way, and we want it to respond to our commands in a good way. And obviously both influence and response are causal concepts. And agency is a causal concept. We argue in a couple of publications. And manipulation, deception, intent, harm, fairness, many of these things are basically consist of some causal relationship and sometimes some comparison between counterfactual worlds. And this is exactly the kind of thing that causality is good at expressing. So that's a little bit about why causality. What I want to focus on today is mainly generalization, result about generalization, which says that an agent that's robust to distributional shifts must have learned the causal model of the world. And that will be sort of the main theorem. Depending on how much question interaction there is, I'll also talk a bit about agency, which is, in our perspective, quite closely related to generalization, and obviously quite related to the topic of this conference. So, but before digging into the actual theorem, I think most people are probably somewhat familiar with causality already, but just a brief recap to set the stage. We say that the one variable, like weather, causal influences another variable, say sprinkler. If an external intervention, changing the weather, say from sunny to rainy, would change Mr. Jones' decision to turn on the sprinkler. And when this is the case, we draw an arrow indicating the causal influence. Both the weather and the sprinkler influence whether the grass turns green, so that's why we draw these arrows. In a causal Bayesian network like this one, each node has an associated conditional probability distribution, like how likely is it to rain or be sunny, how likely is Mr. Jones to turn on the sprinkler in different weather conditions, and how likely is the grass to become green for different settings of weather and sprinkler. If you multiply these together, you get the joint distribution describing your entire environment. And then, of course, you can also do interventions. So, for example, if you want to make an intervention and change the sprinkler, then we're just changing the mechanism associated with the sprinkler. So, for example, we might change this conditional probability distribution with a, say, delta distribution, whereas it's always on. And then we just update the joint like this. So in a sense, a causal Bayesian network doesn't just express how the world is, it also expresses how the world could be under any possible kind of intervention. So it's a whole collection of joint distributions in a sense. One final note about background, we borrow from the influence diagram literature, because we work a lot with agents, and so we draw decisions with square nodes, and the thing they optimize with diamond nodes. So, for example, the sprinkler is turned on in order to make the grass green. I'll say more about that later. We'll talk about agency. Okay, with that bit of background, let's go to the main topic, generalization. So the first question or like distinction we need to make when talking about generalization is whether it's IID generalization or out of distribution generalization. Traditional machine learning is IID. You draw training and test points from the same distribution. That's fairly well understood. But we're more interested in auto-distribution generalization, where, for example, you train your self-driving car in one city, and then you try to drive it in another city. Or you train your chatbot in some controlled environment, and you deploy it to the internet. And when you try to study auto-distribution generalization theoretically, the first question you need to answer is, if the training distribution is different from the test distribution, why is learning possible at all? If these are different, how is learning possible? So there has to be something that's similar between the two. And the answer causality gives to this is that really what's changing between the training distribution and the test distribution is that we make an intervention on a small number of variables. So the most causal relationships stay the same, it's just that a few interventions have been made. So we can illustrate this with a sort of classical image classifier misgeneralization problem, where we have pictures of wolves or dogs that are pictured either on snow or grass background. And if wolves are usually pictured on snow and dogs usually pictured on grass, the classifier sometimes learn to classify snow versus grass rather than wolf versus dog. So first we draw a diagram of the situation. It can either be a wolf or dog, it can be snow or grass, and this can be correlated in some way, maybe by location, say. The foreground object and the background together determine what kind of distribution over images you have. But the true label is a function only of the foreground object, because that's what we wanted to classify. The predictor only sees the image, and it gets a loss depending on how well its prediction matches the true label. So this kind of diagram could represent the training distribution. And then at test time, we might see a dog on snow. And we can represent this by saying that at test time, we have had an intervention, which I denote with sigma. Saying that, say now all pictures are talking on snow, and suddenly we can have a dog on snow, and then the predictor might get it wrong. But most causal relationships stay the same. It's just something that changes, but most things stay the same. So I think that's the first way that causality is useful for generalization. Sort of clarifies in which way do we expect learning to still be possible, even though the test distribution is different from the training distribution. The second question is whether the system itself needs to have a causal model of its environment in order to generalize to distributional shifts. There's a quite vivid debate in the machine learning community around this. And on the one side, we have people from causal machine learning that argue that surely a model needs to have a causal understanding of the world in order to be able to generalize properly. And they publish lots of papers at the big conferences, and it seems like causality is really helping them. And there's also evidence from psychology literature that humans use causal models to understand the world, and that's how we can generalize. But on the other hand, we have things like GPT and large language models that are quite robust and can handle quite a range of distributional shifts, even though they have not been trained with like causal inductive biases or anything like that. So that raises the question, is causality really necessary for generalization? And the main theorem that I want to present today is wants to answer this question: yes, causality is necessary. It's not possible to generalize to distributional shifts if you don't have a causal model of the world. To do that, first need a little bit of setup. So first, what do I mean with a generalization problem? Basically mean this. For a given intervention sigma, this is the way we formalize the generalization problem. For a given intervention sigma, should return a policy with a bounded regret that has bounded regret in the modified environment. And you can of course tweak this by changing what kind of interventions you consider and what kind of regret you require, but it's the general form of generalization problem. Okay, then I also need to.
So,
yep.
we're showing the policy of the intervention because the policy is parameterized by the intervention?
Yes, thanks, that's a good question. I meant to say that. So here, this is a little bit different from, or this is an idealization of how generalization usually looks, because if, for example, the main adaptation, you get, maybe the agent gets to see a little bit of data from the new environment. That and other things like zero-shot learning gets just like a label maybe of the new environment. But here, in a sense, we're making the problem easier because we're telling the agent exactly what change did I do to the environment that it's not supposed to do, and we're requiring it to have bounded regrets. Yeah. So actually, we're making the problem easier because we're telling the agent more than it usually knows. I also need to slightly generalize the notion of intervention. So here, often when we say interventions, people mean hard interventions, where, for example, you set a particular variable to a particular value, but you can also consider more general classes of interventions, which replaces the mechanism here with some other mechanism, P prime. And then you can even use some different parents if you can, without creating cycles. But for example, you can use the same. So this allows us to change the environment in many more ways, and we want to do that. The problem with these kind of soft interventions is that they basically give away the structure of the environment, and we don't want to tell the agent that. So as a kind of compromise, we use something called local interventions, where basically we first record what value x took if it wasn't intervened, and then we apply a function to this value, and this is like the x prime that we intervene. So basically, local intervention is a function setting x to some function of its original value. It's a special case of a soft intervention. It's not too hard to show. These local interventions are deterministic because it's just a function. So to introduce some stochasticity, we use mixes of these kind of things. So basically, a mixed intervention is some probability for a number of different interventions. So basically, P of this mixed intervention is just like the sum of, you basically flip a coin and pick some intervention in the mixture.
For your local interventions,
yep.
Are you allowing addition of new arrows?
No.
Okay, so you can delete arrows but not add.
Yeah, because basically this is the original value of x, right?
Yeah.
And we only let the new value depend on the old value of x. So we're basically not interested.
So it has to factor through the old value?
Yeah.
Oh, okay, that's pretty, all right. Got it.
That way we're not revealing any structure of the graph to the agent when we're doing this intervention. Yeah. Okay. I think I'm now ready to state the theorem, which I should read from my notes so don't get it wrong. The theorem is restricted to passive decision tasks because it was slightly easy to prove it. So in a passive decision task, which I'll say what it is, basically we just have that the utility is a child of the decision, like here. There are not nodes mediating the effect of the action on the utility. It just makes the proof easier for some reason. So in a decision task, in a passive decision task, from a policy oracle gamma that maps interventions to a new policy for the modified environment. And pi sigma has the regret. Pi sigma is less than some delta. We can infer an approximation of the true causal Bayesian network, and importantly, the approximation error goes to 0 as the regret bound goes to 0. So if you have an agent that generalizes perfectly, you can fully infer the entire causal Bayesian network just from the agent's behavior.
So, sorry, what was, I think I missed this. What was
Yep.
a passive decision task?
Sorry, I mentioned this briefly. It's where the utility function is a direct descendant of the prediction. So there are no nodes mediating it. It says here. So the utility is a child of the decision. And this, for some reason, you can have interventions that break the thing otherwise. There's some technical reasons which I forget, but it's just easier to prove in that setting.
Do you use false without that assumption, or you just...
I think you need some other kind of assumption to replace it. Yep.
And you're saying you can infer.
So there's some true causal Bayesian network describing how the world works.
Okay, yeah.
I'm saying that I can just look at this policy and how it adapts. So basically we have some policy here, right? And this policy adapts to the kind of changes we make in the environment. So I'm saying I can just look at how this generalizing agent that can sort of adapt to different changes in the environment. I just look at the behavior of this agent. And from just the behavior of this agent, I can infer the entire causal graph, and I can infer all the mechanisms as well, all the conditional probability distributions.
And you can, and the correct factorization.
Yep.
It's not that I can have, right, so probability distributions can have different factorizations for different underlying causal graphs, but you find the right one.
We find the right one.
Well, if I understand correctly,
Yep.
you've put it in because you've assumed that the class that it's robust to matches this network.
I'm not sure. Can you restate what you said?
What do you mean by class robust to? Sorry.
We're quantifying over this sigma here.
Sorry, yeah, this is from a policy oracle. And this maps, this should be like for any mixed local sigma. That's why I put this there. So it has like, it proposes a regret bounded policy for any mixed local intervention.
Sorry, could you say again what the policy oracle is?
So the policy oracle just maps an intervention to a policy for the modified environment. So like normally you think of an agent as just a policy, right? Mm-hmm. But now I want to think about the generalizing agent. So this is basically policy in any shifted environment.
I see.
Yeah, so the policy oracle just captures that.
And why do you call it an oracle? Is it not, it's computable, I suppose?
Yeah, why do we call it an oracle?
Because you can query it and get results back.
Thank you.
You can take policy and be like, what would you do if things change like this? What would you do if
So
things
you
change
can
like this?
counterfactually.
What would you do if things
Okay,
change like that? And if it reliably gets low regret, then that lets you back out that lets you infer the causal model that it's implicitly using.
Okay.
If I understand it correctly.
Yep, that's a very good summary. Thank you.
I
Oh, sorry. Yep.
So, if you were, let's say, that you're interacting with some system, and then you have to, probe it with interventions, is there some sort of thing you can say about, how many, how does my approximation error decrease as the number of probes goes to infinity?
Oh, how many times do you need to query the system to get the graph?
Yeah.
Could you summarize it?
Or the question. So the question is, here we assume that we can query the policy oracle with any intervention, and if we can query it with all the different interventions, which are infinitely many, then we can get the causal Bayesian network back. David's question is there some finite number which we can get an approximate? I don't think we have a result about that. Basically, the trick that we're using is to use this sort of mixed interventions in a kind of Savage style way for Morgenstern phenomenon to figure out exactly the probabilities that the agent puts. So I think we're probably fine with a finite number of queries, but exactly how many, I'm not sure. Yeah. Good. Yeah, so I'll next discuss, once people have adjusted this, I'll discuss some implications that we think are interesting. Yeah, so the first sort of obvious...
Can I just ask one more question?
Yeah, please.
So I think for me the question of how significant I should think this is to do with how well the notion of interventions we're using captures distributional shift or whatever. So if I think about it in one way, I'm we're saying if a policy or if an agent is robust to a bunch of distributional shifts defined in terms of a causal graph, then we can infer that causal graph from the policy. But yeah, do you think that is the right way to define distributional shifts? That captures all of our intuitive notions of distributional shifts?
I don't think it captures all the different notions of distributional shifts, because it doesn't capture things like what we introduce a new variable or we change the structure of the graph. There are a number of things we can't do with interventions. But that again is we're underestimating the difficulty of generalization here. Because we're just saying an agent that's robust to at least this class of distributional shifts must learn a causal model. Ideally, we would like the agent to be robust to even more shifts, but at least it's robust to this.
Maybe a trivia question at this stage, but would you then say that you might have a system that is an agent conditioned on a class of interventions, and the same system wouldn't be an agent on a, say, larger class of possible intervention? Is it a relative definition of agency?
Yeah, this is not really a definition of agency yet, I would say. I was trying to get to definition of agency in the second half, so maybe that's a better time to answer that question.
Okay, yeah.
Great.
Yeah, I guess, I don't know, I want to poke at this. I don't quite have the right example, but I mean, I think about something I don't know, thermodynamics, where I'm not working through what do the particles in the gas do, and so then I'm what happens there? It's well, if you tell me, you move this particle, I don't have, I'm not really robust to that. I don't know how to account for it, but maybe I'm still reasonably good because, moving one particle doesn't matter very much.
Yeah, no, that's a great question, because the kind of graph I've drawn here is quite a high-level graph, quite high-level concepts. And I'm saying a distributional shift corresponds to changing one of these high-level variables. And an agent that's robust to changes in these high-level variables must have the graph in its head of these high-level variables. But it doesn't necessarily have the graph of the low-level variables, because we haven't said that it's going to be robust interventions on those low-level variables.
Yeah, so I guess like we can sort of, we could have a family of graphs that we all think describe something about the situation that the agent is dealing with.
Yeah.
And in one graph, it might have good regret on all of these, and another it might have bad.
That's right.
And I guess I'm also thinking like, well, maybe there's a kind of description of what changes it's robust to that doesn't come from a causal graph, but is just some other family of shifts.
Yes, that's right. Yeah, so the graphs, the shifts it can handle, those are the graphs that it knows. Let's see how we're doing. Cool. So, right, so let's do a few interventions. So the first one we basically talked about, like, really we're just saying that we can infer the causal graph from the behavior, but we interpret this as the agent must have the causal graph in its head in some sense. We don't know how it's represented, but somewhere inside it should be the knowledge, because we can infer the knowledge from the agent's behavior. Second implication is that if your training distribution is broad enough to include many distributional shifts, then basically the only way to get a low training loss is to learn the causal model. So basically it's enough to have a wide enough training distribution to encourage learning of causal models. You don't really need any special causal inductive biases, you just need a wide enough distribution. And I guess is that this is what happens with large language models. They train on very large distributions, and there are some make interpret results that sort of suggest that they do learn causal models, like the recent world map result. Like you can basically find like longitude and latitude inside a network somewhere. So I think it sort of checks out with what we know empirically. Another implication is that sort of robustness implies task general intelligence. In some, not the formal way, but loosely, because if you're robust, you must have a causal graph in your head, and if you have a causal graph in your head, then you should basically be able to optimize any function of that causal graph. So you should be able to learn many different tasks. In particular, we're quite interested in this kind of path-specific objectives, where you tell the agent to optimize some objective via some causal paths rather than others, as a sort of safety feature. And it seems like robust agents should have a causal graph in their head, so they should be able to learn this kind of graph. Finally, and I guess I'll just discuss this before the break. Since you must have a causal graph in order to be robust, if your training data is not good enough to teach you a causal graph, you will not be able to be robust. And this explains like the coin run Goldman's generalization example. So basically, coin run, you train an agent in some sort of Super Mario-like environment. The coin is always on the far right. And then you think the agent has learned it because it always gets the coin. But if at test time you move the coin, you find that actually the agent has just learned to go to the right. Has not learned to get the coin. So this looks something like this. We have a coin position. You have the agent's actions. And you have whether you get the reward, whether you find the coin. But what happens in the sort of standard coin run Goldman's generalization case is that this coin position is always the same place. And this means that coin position is a constant random variable. And a constant random variable is independent of all other variables by definition. So this means that the graph is unfaithfully close because there is this edge between two variables, but these variables are independent in the distribution that you see. So the distribution is unfaithful to the graph. And it's well known that if you have an unfaithful distribution, it's impossible to learn the graph. And that's why the agent fails to generalize. So I think on that note, we're just about on time for a little break.
Great. Okay, I have 23 of you. There'll be 19 spots. And Nora will lead a sprint breakout session in the kitchen room. So I want you all to leave the room. Yeah, John?
Probably fill some of these spots with something.
Okay, but unless you have questions for Tom, I want you to leave the room to the kitchen.
The golden will
What are you going to
rain.
talk about in the second half?
In the second half, I'll talk more about agency.
Okay.
Yep. Right, so we pretty much covered what I wanted to say about generalization. I thought in the second part, I will talk a little bit about agency instead, which is quite closely related to generalization in our thinking. And maybe we can answer Manuel's question as well. So basically, agency for us is goal-directedness. You're trying to achieve a goal. And what does it mean to try to achieve a goal? One way to operationalize that is to say, like, well, if the world was a little bit different, you would adapt your behavior so that you still achieve the goal. So in that sense, agency and goal-directedness is actually very closely related to generalization, because it's exactly these kind of small changes to the environment we're considering and wondering, does the policy appropriately adapt so that it still gets the goal? But I think it's nicer to discuss this in the context of Mr. Jones, who's clearly an agent. So let me just redraw this one a little bit. So let's just focus on the sprinkler and the grass, whether it's becomes green or not. And then we can consider, just like we did there, like distributional shifts. What if someone came and replaced the lawn at Mr. Jones' house with something that required less watering, say, and Mr. Jones was somehow aware of this, well, then his policy would adapt. So for us, this is basically the structure that defines agency. Agents are systems that adapt to interventions on the environment. As I've drawn in here, I've basically drawn a causal arrow. But to make that precise, we have to like slightly reinterpret these interventions and policies. So we basically say, before I had this like distribution, right? P of G given S. And I changed that with an intervention. That's what the intervention changes. But really, I can just say that this is a node. The way that grass responds to the sprinkler is a node. It's like the grass mechanism. And I can also like reify this policy, so it's actually a causal node. And once I've turned these things into nodes, sorry, the second half is less prepared than the first one. Let me start from a slightly different way. If you want to test how this agent adapts to interventions, there are basically two kinds of interventions we need to keep in mind. The kind of instantaneous interventions that happen after Mr. Jones has already made a sprinkling decision. Let's say Mr. Jones decides to turn on a sprinkler and later we go on and intervene in the world and make the grass green. There's no way Mr. Jones can adapt to that kind of intervention. But there's another kind of way that we can intervene in the world, and that's like by replacing Mr. Jones' lawn and telling him that we do it. In that case, Mr. Jones has the ability to adapt. So there are basically two kinds of interventions. there's like the instantaneous, or sometimes we call them pre-policy. No, sorry, post-policy. The agent cannot adapt its policy to them. And we also have that sort of permanent or post or pre-policy, which an agent can adapt to. And we can basically interpret these two kinds of interventions as interventions on different nodes. Since there's no arrow from this node, there's no way that an intervention here on this node can influence the sprinkling decision. But since we do allow, but if we instead intervene on this mechanism node, there is an edge, so the policy can adapt. So basically we interpret by sort of reifying these interventions as nodes, having the mechanisms as nodes. We can distinguish between pre-policy interventions, which are nodes that the agent can adapt to, which are nodes from post-policy interventions, which the agent cannot adapt to. Okay, so what is an agent now? In our thinking, an agent is characterized by three things. It needs some degrees of freedom. Has some options available to it, so that it can do this or can do that. And this is a little bit confusing because in a physicalistic universe, everything is determined by the laws of nature. But at some higher level of abstraction, there is a sense in which I can go to the left or go to the right. And that kind of freedom, whatever that freedom is the kind of thing that an agent needs to have. So with right degrees of freedom. This choice of the agent has to influence the world, so it has to have some influence. And finally, the influence has to be directed towards something. The agent has to be goal-directed, trying to achieve something with its influence. And the way we operationalize that, as I mentioned briefly before, is adaptation. And adaptation is basically this kind of causal effect. If we change the world in a way that the agent has a chance to adapt to it, will it adapt? Sometimes people find counterexamples and say like, aha, I can find this particular causal structure in some non-agentic setting, but if you make the graph a little bit bigger, so for example, maybe the point of the sprinkler is that the grass becomes wet, which in turn makes the grass green. So maybe this should not be W, this should be G. Then we would expect this kind of structure. So we would expect Mr. Jones to adapt if we made it harder to make the grass wet, say, then he would water more. So he would adapt to changes in the mechanism for wetness. And if the grass required more or less wetness to be green, then we would also expect him to adapt. And again, maybe you can find this causal structure somewhere else. That's not an agent. But what you can also do is you can, by an intervention here, you can cut this edge. And once you've cut this edge, if Mr. Jones was really an agent and all he cared about was making the grass green, you would expect him to stop adapting to changes in wetness. So in a slightly richer causal graph, you can get quite a few conditions that sort of indicate goal-directedness and now pretty much rule out everything else.
So I'm trying to...
Yep. Yeah, sorry, this is quite involved and complicated.
So you're saying if I could just have these four things, so that the simpler thing, that isn't maybe quite agents. You can have counterexamples, intuitive counterexamples. Could you give one? Could you name something?
Matt, help me. What is a counterexample?
I don't know, you can construct it. Imagine like a block on a slope and then like there's enough friction so that it doesn't move. And then imagine like, I don't know, this is like the mass of the block or something, and this is its acceleration. And you increase the mass, but the friction increases such that the acceleration doesn't change. So this is a little bit like the mechanism of the acceleration is the friction, and yeah. I'm not sure if I said this exactly right or if I...
Yeah, we should have had a counterexample. Manuel, you had a counterexample for me yesterday, I think.
Probably a few. I mean, in general, you could just say that, the class of, say, modifications, interventions that you apply is still, say, larger than the things that you can actually do. Like, say, there might be conditions where no matter what you do, the grass will never grow.
Yeah.
And I don't want that necessarily to be a criteria for agency, I guess.
Right. Yeah, I mean, I don't know. I think at some point we had counterexamples, but I can't remember them now. With more structure, we have a theorem under some assumptions, which I also won't state right now. You get always the right thing. And this is the discovering agents paper, basically.
So there's some counter yet to be specified down. There's some counterexample for this 4 thing. And then you're saying, if it really cares about...
Let's assume it just cares about the grass being green.
Yeah.
What's the kind of consequence of that? That means like if we somehow manage to separate greenness from wetness, so that the wetness no longer influences greenness,
Right.
then Mr. Jones would cease to trying to make his lawn wet. Because there's no point for him to make the grass wet anymore.
Okay.
Yep.
I think I remember what we were talking about, but feel free to interrupt me.
Okay.
It's not relevant. Say if I have like, I don't know, some... funnel, or I like to think even simpler, like I have a ball, that rolls down to the bottom of something. You might want to change the initial conditions and it will still roll to the bottom of something. And there are changes that you can apply to this particular system such that it will roll down in a slightly different way, but it will still get to the bottom of it. Even say if it's not necessarily smooth, you might want to make it a bit more rough or something, it will still roll down. And I think that could probably fit.
Yep.
And it's not an agent. Okay. Yeah, thanks.
Thanks.
I'm not sure that's like a terrible counterexample for this. And I think there's probably more problematic counterexamples where, like, in some sense, a ball rolling down a hill, it's like some kind of trivial optimizer. So maybe it's okay to your definition of agency to say that. But like, I think you can also write down this causal structure where it's like intuitively not like that at all. And it's like maybe we need more than just the causal structure. Maybe we need to think about. Well, maybe we need more than just the arrows. Maybe we need to think a bit more about the details.
Cool. Yep.
If I echo this back, something like there are optimizing processes or equilibrating processes that you might not want as agents. And so this proposal is, look, if I give it a broader range of perturbations and it continues to re-equilibrate, that begins to move us more towards something that we do want to manage. So let's say I take the ball out of the funnel and I move it to the other room, or I ship it to Australia and my person brings it back.
Right.
Then you're like, now it's looking less like a funnel and more like an agent.
Yeah, I think that's right. Yeah. Yeah, because I think for us agents is goal directedness. The things that really push towards one thing is agents, and we can try to operationalize that, but like modifying the environment. But of course, agents is not a binary, like you have more or less agentic things. And it's kind of natural to measure this kind of agenticness in this kind of graph. If I remove some distractions. Because you can consider what range of interventions does the policy appropriately adapt to. If it's a wider range, then it's more robust, more agentic. How quickly does it adapt? For example, humans are quite good at adapting quickly. You tell them it's cold outside and you put on a jacket, whereas, for example, a clam can only adapt to a revolutionary timescale. So in that sense, a human is more agentic than a clam. Of course, you can consider how optimal is the policy for the particular objective. More optimal policy might be more agentic. How much information goes into the decision. We had like something from above. How much freedom is there involved in the decision? What the range of things, maybe like simple robot can only move its arm left or right, but a human has like all sorts of things at their disposal. How much influence do you have on the world? So I think a number of things that sort of quantify agency in some sense can be captured in these little diagrams. And that's perhaps one future direction that I'm kind of excited in. Can we turn this little picture, this story, into a more quantitative measure of agency? And can we understand how different kinds of artificial agents would contribute or detriment various aspects of human agency? That's like a little research program that's hoping to pursue. So let's see.
You have 15 more minutes.
15 more minutes. The final thing, so that was it's a bit about discovering agents, a bit about dimensions of agency. Maybe one more thing that's interesting to discuss is emergence of agency. It sort of illustrates how we think about agency as this kind of feedback loop. Somehow the goal feeds back to the behavior. So I think most people here would be familiar with the sort of actor-critic kind of reinforcement learning algorithm, where you basically have two systems. One is a critic, whose job is to just predict how good any given action is. And the other is the actor, and its goal is just to satisfy the critic. So in a sense, we have two quite simple systems, none of them particularly agentic because they just have quite simple objectives, but together they form something more agentic, which is like a whole reinforcement learning algorithm, which could be arbitrarily powerful. And I think there's a cute way of explaining this kind of emergence.
Sorry,
yeah, go on.
The critic predicts how much reward an action is, and the actor tries to
get the critic to like its action.
to like it.
To like say that this action will probably give a high reward.
And how does it do that? Sorry, maybe I'm stupid. Like, I don't know this.
So you think of the critic, do you know critic as a Q-learning?
Yeah.
So the critic is basically like a Q table. It says like for every action, what's the expected reward?
Uh-huh.
And it has learned this from like seeing past interaction with the environment.
Yeah, I see.
And the actor is basically just like looking at the Q table, where's the highest value? Okay, I'm gonna pick this action.
Right, okay.
Yep. So how can we draw this with the diagram? Well, we have the actor taking actions. We have the critic outputting a Q table. The actor is just trying to pick the highest value in the, I'm going to use different colors. The actor picks the action. And it's just trying to optimize what the Q function says about its action. But the action also influences the state of the world, which influences which reward the agent gets. And the Q function wants basically what it says about the action to match what actually happens to the action. So it experiences some kind of loss based on the difference between the two. Need one more color. So the Q function decides on the Q table, and it's trying to optimize the correctness of its prediction.
So what I call critic, is it trying to, what is it criticizing?
It's criticizing the actor, basically.
Like imagine I'm trying to suggest ideas that you'll like, but you're trying to assess my ideas objectively based on whether they'll work. Like you are the critic, I'm the actor.
But I thought the critic suggested.
No, the actor suggests the ideas, the critic says whether they're good.
I see. Okay.
So in this context, how much reward they'll get.
But does the critic predict how much reward you'll get?
Yes.
And then you actually do it, and then if the critic is close, they get points, and if they're far, they lose points.
Yeah.
Okay, got it.
Cool. So this is the causal diagram. I think what's interesting for me here is that how non-agentic in some sense both the actor is and the critic is. The actor doesn't care about the state or the reward or anything. It just cares about satisfying the critic. It's a very simple function. Just look at the Q table, which action has the highest expected reward. And the critic, similarly, just cares about getting the right prediction. It also doesn't care about getting more or less reward. But somehow the system as a whole is acting agentically as if it's trying to control the state and optimize reward. And we can explain this with this kind of feedback loops. Because imagine what would happen if we made an intervention to the reward function. So now the system as a whole was rewarded for other things. What would happen then is that the Q learner will output a different Q table. And if the Q learning was outputting a different Q table, well, then the actor would output a different action. So we can see that the same structure that we had here, that sort of the goal influences the behavior, is exactly the same structure that we have here. We have that the goal, the reward, is influencing the behavior. So in a sense, looking at the system slightly more abstractly, we can say that actually the system as a whole is adapting its behavior to optimize the reward, even though neither of the components cares about the reward.
Doesn't the critic care about the reward?
The critic, in some sense maybe, but there is no causal path that goes sort of via reward to its reward.
Oh, because it doesn't affect the reward, right? Yeah.
Yeah.
Cool.
Wait, but like the critical one needs to see the reward in order to learn how to judge it, right?
Yes, that's right.
It feels like that should be represented as some kind of causal thing.
I mean, in a sense, it is this thing that represents that. This is like an instance of, this is like one-shot environment. What happens is Q function, actor, that leads to some state, leads to some reward, leads to some loss. This is like what happens at one time step. This purple thing more represents like the learning that goes on over multiple time steps.
Yeah.
So is the agent like some part of this graph, or is it the whole thing?
Yeah, that's a very good question. What is the agent? This is the decision, like this is the decision that the actor takes, but it's also the decision that the system as a whole takes. And the system as a whole is trying to optimize this thing. We can use purple maybe. But beyond that, I don't really know how to talk about this higher level system.
It seems like in training you need both the actor and the critic
Yep.
to like make the agent, and then in deployment just the actor.
That's true. But you wouldn't get the adaptation without the critic. Yep.
Yeah.
So in a sense, it's only agentic with the critic.
So the point is like the actor in some sense cares about QA, the critic cares about loss. The combination of these is that the system as a whole cares about the reward.
That's right. Yeah.
You actually have 7 more minutes. I made a mistake.
Cool. Okay, I'm actually sort of other things to say, so I'm happy to wrap up there and take questions. Thanks so
All
much.
Let's thank the speaker. Very rare.
I know.
Makes my job very easy. Let's.
Yeah, so one worry I might have here is that what is an agent? Like, this is not truly embedded, so to speak, in the sense that the information channel through which the agent, the policy, learns how the intervention in the environment is not part of the environment itself, right? Because it's in this different level. I don't know what exactly an example of this could be, but it could be something like the agent learns through some mechanism in the real world that the intervention has happened, but this mechanism itself that has provided the information for the agent also has other causal interventions in the world and so on, and breaks some things. Yeah, and actually I think that's also related to Abrams update versus meta update, because kind of the agent should update on the fact that this has happened instead of just the information. But yeah, why do you think this is not a problem? Or if you do, how do you plan to fix that?
Did you get the question? Can you summarize it for me?
Oh,
Sorry, that was a long question.
it is a long question. How can I summarize that question? I think your concern is that the sort of mechanism by which the agent adapts its behavior is not really represented.
Exactly, in the environment.
Yeah. I would say that it is represented. It's just represented at a very high level. Because we say that somehow the change in the world influences the behavior. There is much more to say about this very interesting relationship, but I think for us the important thing is that the relationship is there. We say that this is agentic when the relationship is there. Exactly how it's mediated can probably be in very many different ways in different kinds of systems. So for example, you could have some sort of clams or evolutionary things, then it's evolutionary condition, which means different individuals survive and you get this kind of adaptation, or you can have powerful AGI and you just get some little bit of bit somewhere and it's just and it updates its policy. Yeah.
Okay, so I do agree you can add more things to get more richness on the left side, but maybe my claim is something like, formalisms with this shape, with the actual separation, will not be able to encompass some realistic situations in which, not only the information channel is rich or something, but actually it has causal effects on the variables that the agent cares about, which are on the right side of here. I'm not sure if that's true, but I think that could be true. That some realistic natural situations cannot be represented in this way.
Okay, I'd be curious to see such such a situation, because I don't know exactly what you mean.
To see an example of
Yep.
this, I'm not sure.
Okay, I'm gonna cut that off.
Yeah.
We should come with it. Sounds interesting. I'm also interested to hear that and what it has to do with meta updates. But are there other questions or comments? Yeah.
So I have a question about the first part.
Yeah, please.
The generalization part. So, okay, maybe this is also kind of not the right perspective to take on that part, but there's this debate about kind of causality and whether, I don't know,
Is it actually necessary?
Yeah, whether it's actually necessary, whether you need it, kind of in philosophy, right?
Yeah.
I don't know whether it's a real thing, whether you need to do causal reasoning to make decisions properly and things like that. So I guess if you come from that perspective, I guess one could look at that work and kind of see it as an argument for the view that one does need causality. Okay, but now, So the high-level thesis, to some extent, is, if I understand correctly, that you need causality to generalize with respect to distributional shift. But then, I mean, the causal relationships are defined as kind of what happens if you make interventions on certain things. And the distributional shifts are also defined as kind of what happens when you intervene on certain things. So like, to some extent, you need to know causal relationships to be robust to distributional shifts. Like to some extent, it kind of says you need to know what happens if you make interventions to be able to predict what happens if you make interventions. Which I guess that you can, like, I don't know, people who are skeptical of causality or something like that would probably agree with this statement, I would hope.
I would also agree with that statement.
But it's kind of less, I don't know, it's less, I don't know, it feels much less philosophical. Like, I mean, the theorem is still like,
it's not a trivial theorem to prove.
The theorem is still definitely non-trivial, but more, like, to me, the thing that I see in the theorem as the non-trivial part is kind of that you can get the entire beliefs from the behavior.
Yes, if I, yeah.
Which is kind of surprising. Okay.
So if I can summarize that, or did you want to say something?
Yeah, I have some comments, but
if I can summarize that, it's like we already encoded changes with interventions, and now we're saying we need causality to understand interventions. So it's like circular almost. And yeah, I mean, as I said, like the theorem is still non-trivial because it's not at all obvious that you could learn entire structure from just observing how behavior adapts. But the other thing is like, but I think this is mostly interesting, philosophically interesting, if you buy this first thing that I said, like, what is generalization? Because if you study out the distribution generalization, you need to somehow answer the question, why is the test distribution similar enough to the training distribution that learning is possible? And I think causality has a very good answer to that, like, namely, the world is a causal, we live in a causal universe, which is composed of many causal mechanisms, and normally what constitutes a distributional shift is like when a small subset of those mechanisms change. And if you buy that perspective on out distribution generalization, then I think the theorem has like the deeper meaning.
yeah. I mean, I guess I'll make some comments that, to me, it seems really clear that this, of course, one needs causality. I guess what people are mentioning, like, want to say is like, well, large language models are very smart. They don't, but they don't do this causal things. I will say a couple things about that. One is it's very hard to measure this, so it's kind of a vibe thing. The second thing is large language models are trained on an extremely rich, I mean, the richest training distribution there is in language, which has been optimized to teach you stuff, and which really extracted a lot of causal information about the world and put it on the internet. And I guess the third thing is maybe a lot of, there are all these results about you can't learn this causal thing, but it seems the real world has certain features where if I use a simplicity prior, I look for simplicity, I sort of find the right causal mechanism in many cases, even though I'm not like, even though there are theorems to the fact that in general it's not possible to learn. I think, that those will be my answers, yeah.
But yeah, maybe just to comment on that, sorry, I'll let you go. I don't think this is opposing large language models learning causal things. Like, I think it's something like this theorem predicts that they actually will learn causal models because the distribution is so wide that it contains many distribution shifts, and the only way to get a low loss because of wide distribution is to learn a causal model. So they probably do learn a causal model. That's what this theorem suggests. Yep.
So I guess, like, I kind of like this line of questions, so I'm gonna put another one along those lines.
Okay.
So, are you committed to causality as in parallel causality implemented by an intervention, defined such and such, whatever? Or would you be happy to consider causality, say, even in a naive physicalist way? So, billiard ball kind of world. To give you an example, if I gave you some system within some cellular automata, a game of life, would you be happy to consider causality in some shape or form in those systems, or are you saying, look, you're not giving me a well-defined distribution, don't know what you're talking about, not interested?
I think Pearl causality works very well in a cellular automata because it's basically like this process, right? You know exactly what to compute every time step. Future is a function of current state. And an intervention is just, you change something in the state and then you can see, okay, what happens in the future. So in a sense, cellular automata does specify a causal Bayesian network or
Interesting. That's not at all how I would think about it.
Interesting.
Yeah.
Okay, I think that was the last question. Let's think.
Thank you.